All right, hello everyone. I hope you're as excited as I am to review enthalpy. This is going to be going over lecture 32, which encompasses Hess's law and standard enthalpies. Start off, here's a little bit of Chris Pratt magic for you. Hopefully this isn't you, but if it is, that's okay. Hopefully we'll get you out of there. We'll try and help you figure out what enthalpy is. So we're going to start off with a little bit of a general overview of enthalpy. So I really like this definition because it kind of makes the transition to the mathematical definition a little easier. So enthalpy is a measure of the total energy of a system, E, and the energy expended to push aside its surroundings to make space for the system. The second half is PV. And then below that, we're going to figure out when is there an enthalpy. So right here, delta H, that's going to be the change in enthalpy. So there's a delta H associated anytime a process has a change in energy or a change in heat. So change in energy, that could be like if you're moving from a liquid to a gas, vice versa, solids, all that good stuff. And then change in heat, if the temperature of your liquid is changing or your gas, liquid, yeah, sorry. And so that's when there's going to be an enthalpy associated. So if we want to get into the more mathematical definitions, here's the general total enthalpy equation. Total enthalpy is equal to total energy plus total PV, pressure volume. And so if you want a reminder of PV, if we go back, energy expended to push aside its surroundings. So that's what PV is. I'm just going to refer to it as PV. Know that that's what I'm talking about, but it's just easier to say PV. So why do we need the rest of these? So as it turns out, total enthalpy isn't all that helpful for us. Enthalpy is kind of an intermediary step to find other things, such as like Gibbs free energy, that sort of thing. So on its own, enthalpy isn't that important. And total enthalpy is even less important because we want change in enthalpy when we go on to solve for those things later on. So the second equation here is just derived from the first. We just throw a little delta in front of everything. So if total enthalpy is total energy plus total PV, the change in enthalpy is the change in energy plus the change in PV. And this can also be written as P delta V. And so that's what, when I start comparing these, that's going to make more sense. So let's do that. Let's compare these. So we find this is an equation we know previously. The change in energy equals heat minus P delta V. And we know that if we combine these equations, we can get to this third equation down here. The change in enthalpy equals heat, which is going to be pretty cool for some calculations we're going to want to do for tests and so forth. But to get from these two to this one, we want to put heat minus P delta V into here. But in order for this negative P delta V to cancel with positive P delta V, this P and V need to be constant. We're not really concerned about V because that's not really going to change on us, but it's really important that these P's pressure are constant. So you're going to hear that a lot. Constant pressure, under constant pressure, the change in enthalpy is equal to heat. And so that's how we derive that, and that's going to be important. So now that we know sort of the setup for general enthalpy, we're going to want to figure out what it's used for. So there's 5 main types of enthalpy. As you can see down here, we have enthalpy of vaporization, of fusion, of formation, reaction, and bond enthalpy. And we're mostly going to focus on formation and reaction. All these 4 are kind of self-explanatory. Bond enthalpy, that's just going to be like enthalpy of breaking and forming bonds. So that's probably also pretty self-explanatory. But if you wanted more of an explanation of this last one and these first 2, I would suggest you go on to review videos for lecture 33, because this one is only going to cover enthalpy of formation and of reaction. So if you're looking for further than that, please go on and study other stuff. So let's talk about this real quick. So we have exothermic and endothermic. And so in exothermic reactions, delta Q is going to be, delta H is going to be negative. And in endothermic reactions, delta H is going to be positive. So this is the sort of idea where were directly related to energy. And so, for example, in an endothermic reaction, we know that we're breaking bonds and it takes energy to break bonds. And so that's why we're going to need that. So, sorry, let me just be more clear about that. So we know that taking energy is positive energy. And we know that if we have positive energy, and PV are just whatever they are, then delta H is then going to be positive. So that's kind of how those are related. You can just refer to this when you know, or hopefully if you're studying, you're going to try and memorize that, but that's going to be a helpful rule for you to follow. So let's talk about standard conditions. So the symbol for standard conditions is this little degree symbol. You've probably seen it a few times. And all that means is that temperature is going to be 298 Kelvin or 25 degrees Celsius, and pressure is 1 atmosphere. And so this can easily be confused with STP, which if we remember from a few lectures back, that was important. But this can be confusing because pressure is going to be the same at 1 atmosphere, but temperature is going to be different. So at STP, temperature is 0 degrees Celsius, but in standard conditions with our degree sign, it's going to be 25 degrees Celsius. So just try and memorize that, try and get that in your mind, because that's going to come up a lot in enthalpy because it is. And so another thing to know under standard conditions is the standard state, and that's the most stable physical state at standard conditions. So for example, if say something at 25 degrees Celsius was most stable in a solid form, then that's its standard state. And standard concentration is always going to be 1 molar for anything. So that's not going to be super important, but maybe just something to note that 1 molar is standard concentration. So that's all I have to say about that. So let's talk about the standard enthalpy of formation. So that was one of our major things at the beginning. We just threw the standard sign of the standard in front of it, but enthalpy of formation is going to be one of our 5 major things for enthalpy. So what is it? Standard enthalpy of formation is the change in enthalpy when exactly 1 mole of substance in its standard state is formed from pure elements under the same conditions. And by the same conditions, we mean also their standard state and the same pressure, volume, all that good stuff. So what does this look like? This is a very specific sort of enthalpy. We need exactly 1 mole. We need its standard state. We need pure elements, and we need same conditions. If you don't have any of these things, it's going to mess with it. And so the most important thing I'd say to look at is that this doesn't have a coefficient. That's what we mean by 1 mole of substance is formed. If this has a 2 in front of it, it's not a standard enthalpy of formation. But because this doesn't have a coefficient, the product, then we're good. And also please note that there's not 2 or 3 or 5 products, there's only 1. So we're having 1 mole of one thing. And because of that, we're going to notice like we don't usually see fractions in our normal chemistry reactions, you know, but because we're looking for that 1 mole, it's actually okay to put fractions here. In fact, you'll probably see fractions there when we're talking about enthalpy of formation, just because it's what's going to happen to get 1 mole. And so don't be confused by that. Just know reactions that are going to be used for the enthalpy of formation are probably going to have fractions, and don't get confused by that. And then, so standard enthalpy of formation is denoted by delta HF. Also, I think I forgot, if it's standard enthalpy of formation, it should have the degree symbol as well. So that's what it looks like. Don't think like it means final or anything. That means formation. And then, yeah, so that's what it is for NO in the gas form. All right, should be good. So let's talk about the next one, enthalpy of reaction, also known as heat of reaction. Those are often interchanged. And so this means the energy released for the reaction as written. So this one is kind of like enthalpy of formation, not really, actually not really at all, but it can really mean just like any reaction. So for any reaction, the delta H of the reaction, such as here, is given. And something cool about this is heat release is proportional to the amount of reactants consumed. And so I showed an example of that right here. So we have kind of the same reaction happening here, but as you can see, this one is half of everything up here. And because of this heat release proportionality, the heat of the reaction is half as well. And so that's kind of a cool thing that happens here. And so yeah, that's that. And something else is that enthalpy of combustion you'll see floating around a lot. It's denoted by delta H com or conv. It's just a type of enthalpy of reaction, so don't get confused by that either. Delta H RXN, if it's combustion, you know, there's excess O2, it creates H2O and CO2. That's just a type of enthalpy of reaction. We just like to get specific with combustion. So that's what that is. Don't get confused by that. So something cool that will often come up for like word problems for this sort of thing is copy cup calorimetry. And that's just because of what I wrote here. It's an effective way to find enthalpy of reaction for aqueous solutions. And so basically when we talk about copy cup calorimetry, you should know that in these types of things, pressure is constant. And so that's cool. We know because of that, that delta H equals Q. I'll just read what's here. It says reactions happen at constant pressure, which means the energy absorbed or released by the reaction is equal to the enthalpy change that accompanies the reaction. So because of that, this isn't going to be super important for this section, but it will be something that comes up. The Q of the reaction, heat of reaction, or as we know, the enthalpy of reaction, because P is constant, equals negative Q of calorimeter. And so that can mean like if you drop a hot metal in there, then we could calculate the enthalpy or heat of the water because that's the calorimeter. And then we can just compare the positive to the negative. It's not super important for this section, but it's something to know and something that's really cool. Okay, so here's some rules just in general for enthalpies. One, if a reaction is reversed, the sign of enthalpy changes. So if you have two things that are the same exact thing, so if we have like C plus O2 equals CO2, that's probably a bad example. But if you go CO2 into C plus O2, the enthalpy is going to change. And so that's just something important to note for math problems. And then we also have, if the coefficients of a reaction are multiplied, sorry for the typo, multiplied by a value, enthalpy is multiplied by the same value. So that's what we saw, let me see if I can go back, right here, because these were all multiplied by half. This was also multiplied by half. And so that's also another cool property of delta H. And again, that all relates to like the proportionality thing. Okay, let's apply it. So let's talk about Hess's law. This one's super easy. It's pretty simple. So I'll just read what we have here. We have delta H standard change of enthalpy of the reaction is equal to the sum of the enthalpy changes of the constituent reactions. So those are all some big words. I've narrowed it down here. The change in energy, or the change in enthalpy, oh my goodness, where'd it go? The change in enthalpy of the reaction is additive. So that's also probably still confusing. I have a little example. It's the same one from lecture, so hopefully you weren't something brand new, but hopefully if we look at an example of this, it'll make more sense. But basically what this means is, actually, let's just go through it. So we have this combustion reaction right here, right? And we want to know the enthalpy of reaction. So the first thing that we want to note is that a property of enthalpy is that it's a state function. And what is a state function? It means that values do not depend on the path. So if we have here these two cars, see this one and this one, starting from the same spot at the top of this parking garage, and we have one that goes out and directly down. We have this one that goes out and around and around and around. if they start and end in the same spot, their path is obviously different, right? But here we see that elevation gain is the same. They both start at the top and they both end at the bottom. So elevation gain here is a state function because it's the same for both regardless of how they got there. So that's what we're going to know for Hess's law, is that because enthalpy, or the change in enthalpy, is a state function, we know that we can take a multitude of paths to get to the same value, which would be, in this case, elevation gain, but in our cases, it's going to be change in enthalpy. So let's look at what we had. So I've just provided us with a little more information here. We have sorry, confuse me for a second. We have the final reaction that we want, right? And we have these two reactions that have all of the components in them. So we have a CH4, CH4, gaseous form. We have 3/2 O2, we have 2 O2 and half O2, we have CO, and we have H2O. And those are all of our components. And we know the enthalpy for both of these. So based on these, we can add them up because, again, according to Hess's law, it can be additive to get the total enthalpy, or the total change in enthalpy for our final thing. And so how does that work? Let me try and draw real quick. So we want to compare the things from one side of the arrows to the other side of the arrows. And we want to try and keep the things that we want, right? So here we know there's a CO2, so if we like draw a line and we add them, this is gonna get messy. Then we're just gonna add straight down, right? And that goes for the enthalpies as well. So we know if we add them up, we're gonna have CO2 on this side and a CO2 on the other side. And since we have CO2 just going to the same thing, we can just cross it out. It's just a spectator in this reaction. And then we have 2H2O, which is exactly what we want, so that's fine. We have a CO, which is exactly what we want, and we have a CH4, which is exactly what we want. So we have all of our things, but let's take a look at the O2. So we have 2 O2 over here, and we have a half of an O2 over here. So if we add them up, we'll have 2 here and 1/2 here. And so 1/2 is going to take away from the 2, and then we're going to end up with 3/2 of the 2 over here. And so we know that when we add it all just straight down, again, because of Hess's law, we're going to end up with this reaction. And so because when we add it down, that happens, we can actually add these just as they are to reach this, which I think is super cool. See all my fancy annotations. All right, let's move on to the next slide. Sorry, this is killing me a little bit. There it is. Okay, sorry about that. So let's talk about the next thing, enthalpy of reaction from formation. So if we aren't given these enthalpies, again, sorry I didn't write the subscript, but the enthalpies of reaction, and we're given instead enthalpy of formation, we can use that too to find the enthalpy of reaction. So how are we going to do that? So let's go through this. We have delta H, which is again the change in enthalpy at standard conditions of the reaction, equals this big fancy thing is called a sigma, which just means summation, which means you're just going to add up everything after it. So everything in blue here, you're going to add up, or you'll just keep adding up, sorry. So it's a summation of N, which is moles, delta H at standard conditions of formation of the products, and the same thing of the reactants. So again, that's a little abstract. Let's try and get a little more into that. We have this example here. So we have CH4 plus 2O2 goes to CO2 plus 2H2O. And so I don't remember if I talked about this earlier, but the heat of formation of just elements in the standard state is 0. So for example, in this one of O2, because it's just elemental, the heat of formation is zero. And if you think about that, that makes sense because there's nothing to form, right? You just have O2 going to O2. Like, it's not like C plus H goes to CH, you know? And so there's not going to be a heat of reaction for that. And okay, so let's take a look at this. So again, we want to start with moles times the heat of formation of products. So here we have CO2 and 2H2O. So we have delta H of formation of CO2 and 2 times the delta H of formation of H2O. Where does this 2 come from? Again, that's moles. And here we have moles. Now let's talk about that for a second. So when we talked about heat of formation, we remember that it's just for 1 mole. Remember, that's so specific, just 1 mole. So if we have 2 of H2O, then our heat of formation is only for 1 mole of H2O. So that's why we need to multiply it out here, right? And so we have our heat of formation of our products minus our heat of formation of our reactants. And so right here we have the heat of formation of CH4 minus 2, once again, the moles, heat of formation of O2. And if you look down here, I just pulled these heat of formations from the appendix at the end of the textbook, but here they are, and here's our 0 from the O2. And so I didn't take that all the way, but if you just add that up, that would be the total heat of reaction for this reaction here. So hopefully that makes sense. So that's all I actually have for you guys. I hope you guys got something from this. I hope you enjoyed watching. And yeah, thank you.